sundial and atomic clocks. Both of them use periodic motion. First one used Earth's motion, second one used electrons' motion. Pendulum clocks can be another example. They had been best timekeeper until 1930s. Galileo noticed pendulum useful for timekeeping and designed pendulum clocks in his last years. However, he didn't build. But Galileo's clocks wasn't perfect. Actually, simple pendulum isn't perfect timekeeper, because when pendulum lose energy, amplitude decrease, so period change. You can say it's simple harmonic motion and angle doesn't affect. However, that's just an approximation for small angle. I will show how period of pendulum keeps same, but first I want to explain some phenomenon with illusion. This is a popular illusion. Dots look like rolling circle. But if you follow a single dot, you can see this is moving a straight line. What's happening? This is called Tusi couple. Circle rolling in twice as big circle. Any point of small circle moves on diameter of big circle. If we add other dots, we can reach our illusion. Nasir al-Tusi found that motion. In 2047, he criticized Ptolemy's universe model and used his finding for explain planet's motion of geocentric model. What if circle rolling on straight line? Now we have so interesting curve, which is called cycloid. Why it's interesting I will tell you, but firstly I want to talk about Brachistochrone problem. The terms derives from Greek. Brachistos means shortest, chronos means time. For example, the ball move is just effect of gravity from A to B. Straight path traveling time should be the shortest, isn't it? In 1638, Galileo Galilei published the two new signs. In this book, he talked about Brachistochrone problem. His answer is quadrant. This is faster because ball accelerates quickly. His answer is good, but not correct. In 1696, Johann Bernoulli posted the problem in Acta Eruditorum, which is a scientific journal, and he sent the problem to brilliant scientists. He made popular the problem because he found so beautiful solution. I will explain his solution, but before that, I want to show another illusion. How is straight wooden piece in balance? Normally rotate and swim horizontally. Actual question is wrong. Wooden piece isn't straight. Speed of light in air faster than water. So when light passes to air from the water, refract, and we think light comes this direction. Ptolemy did an experiment on refraction in about 160. Results from 5th book of Ptolemy's Optic. He noticed when incidence angle increase, refraction angle too increase, but he couldn't find exact relationship. In 984, Ibn-Sahl found law of refraction. Orange line is light way, and if we extend refract way, navy blue line occur. If we say L1 to incidence ray and L2 to navy blue lane, L1 divided by L2 is constant. We can put angle. Eventually, sine of theta 1 divided by sine of theta 2 equal to constant. In 1600s, this law rediscovered in Europe. Thomas Harriot found in 1606, but he didn't publish. Willebrord Snellius discovered in 1621. He didn't publish, but another Dutch scientist, Huygens, attributed the Snellius work for his light radius. In 1637, Rene Descartes found this relationship. Generally, this law is called Snell's law. We can calculate refraction, but why does light refract? And what is the constant? Ants don't follow straight path because walking on green place hard and slow, so they reduce path lengths on green place. In 1650s, Pierre de Fermat explained refraction with the similar logic. Light goes on the fastest way, which is known as Fermat's principle or least time principle. If you minimize slow path, now total path lasts long, so we must balance it. When time function equal to minimum value, ratio of angle equal to speed of light in first medium divided by speed of light in second medium. This is the constant. Generally, you can see Snell's law like this. Now let's turn back to Brachistochrone problem. Johann Bernoulli used Snell's law. Imagine, ball can behave like light. But ball continuously accelerates, so we must have thinner layers, and thinner, and thinner. And that will be cycloid. Well, I put balls different place on Brachistochrone curve. Which one first reached the bottom? Yes, simultaneously. Brachistochrone curve is as same as Tautochrone curve. From Greek, tauto means same, chronos time, you know. This problem also known as isochrone. Iso means equal. Actually, we back the beginning of the video. I said simple pendulum has problem. In 1656, Christiaan Huygens solved the problem and made first pendulum clocks. He added barriers. Thus, Bob oscillates on cycloid. Lastly, what is the shape of barriers? Probably you give the correct answer. Yes, it's cycloid.